morning, everybody. Here on this slide, you can see also the other authors that collaborated with us in this work within the project What's Up Switzerland, Encoder, Tatyana Samardzic, and Elizabeth Stark. So we're talking about encoder-decoder methods for text normalization, with particular focus on Swiss-German WhatsApp messages. First of all, what is text normalization and why do we need it? So the goal of text normalization is to convert non-canonical text into a standardized form. We know that in natural language processing tools and applications, we need standard text as input. And if the text that we have is not non-standard, then we resort to text normalization to convert it into a standardized form. When is text non-standard? Well, for example, in historical texts, or in dialects and languages with no orthographic standard, and also in computer-mediated communication. In the case of WhatsApp messages written in Swiss German, we have two of these domains combined, because Swiss German is a dialect and it doesn't have an orthographic standard, and because WhatsApp messages are an instance of computer-mediated communication. So, we identified several factors that contribute to the high degree of variation in the source text. The first factor is the so-called dialect factor, which is due to the fact that Swiss German is a dialect, or maybe I should say a family of dialects, with a lot of regional variation, and it doesn't have an orthographic standard. As a consequence, the same word may be written in many different ways, and this is just an example from the corpus that we have used to train our models. The word feel is found in 8 different spelling variants, and here you can see also the frequency for each variant. And they all can be mapped to one single normalized form, which represents them all. The second factor that contributes to the high degree of variation of the source text is the CMC factor. Computer-mediated communication is a form of communication which lies between the spoken and the written medium, and is characterized by a number of peculiarities, like, for example, vowel reduplication that is used to emphasize a word. Like in this example, the normalized word ganz is written with many A's by a user. We have omitted vowels, which is a common strategy to save time. And we also have typos, unconventional casing, and unconventional abbreviations. What is the state of the art? Text normalization is normally commonly viewed as a machine translation task. And in machine translation, neural networks have nowadays replaced the traditional statistical systems as the new state of the art. However, in text normalization, neural networks still lag behind. They struggle to achieve state-of-the-art performance. And what is that? After all, I mean, if the two tasks are so similar, text normalization and machine translation, how come neural networks perform so well only in machine translation? And the main reason lies in the size of the corpora. So the machine translation is very popular, and it has a lot of applications for diplomatic, cultural, and commercial purposes. So new corpora are created every day, and they just grow in size every day at zero cost for the NLP community. By contrast, in text normalization, corpora have to be created ad hoc, usually by experts, scholars, manually normalized, and this can be expensive and time-consuming. And that's why corpora for text normalization are usually of limited size. And we know that neural networks can express their full potential when they can rely on a large amount of data. So talking of data, here are the two corpora that we have used to train our models. We have a corpus of WhatsApp messages created within the project What's Up Switzerland. And the messages are written in all the 4 national languages of Switzerland, but the portion which is relevant for our experiments is, of course, the Swiss-German messages. And a portion of them has been manually normalized. And then we have the corpus of SMS messages. And we have used this corpus to train additional language models. So we use only the target side of this corpus. And we train additional language models, and we will elaborate a little bit more later on how we did this. So we have 2 aligned corpora, 2 parallel corpora, which are aligned, and on the source side we have Swiss German, on the target side we have the normalized form. And the most common alignment unit is the one-to-one alignment. So one Swiss German word and the corresponding normalized form. But we also have cases of one-to-many alignments. This is due to the tendency that Swiss German has to merge words together, like article and preposition, or verb and pronoun, for example. And then we have some rare cases of many-to-one alignments and many-to-many alignments. We have established a baseline for our experiments, so a minimum threshold that we want to achieve in terms of performance. And the evaluation metric that we use is accuracy. So we just measure the proportion of units that have been correctly normalized by our models. So the accuracy has been established as follows. For each Swiss German word in the test set, we look at the training set and we choose the most common normalization form. This results in 3 categories of words. We have unique words, which are always normalized the same way in the training set. Then we have ambiguous words, which have more than one normalization form. And in this case, we choose the most common one. And in case of type, we choose randomly. Finally, we have new words, which are words that have not been seen during training and we just copied. And this method produces an accuracy of 84.45%, which is our baseline, and it represents a very strong baseline to beat. So the 2 methods that we have used are statistical machine translation, so the traditional method, and neural machine translation. And what they have in common in our experiments is that we decided to work at the character level. Character level machine translation is particularly suitable when 2 languages are similar. In Swiss German and its normalized form, we have many word pairs that are formally similar, like in this example, Swiss German Sonne that becomes Sonne. And we have many word pairs that are characterized by regular transformation patterns, like, for example, the pattern II that becomes EI, and we have some examples here, Zieht Zeit, Bitte, Weiter, Please, Preis. And the good thing about character-level machine translation is that once the system has learned a transformation pattern, it can apply it to words that have not been seen during training. And this is a limitation of word-level systems, that when they see a word that they haven't seen before, they just copy it. So this is our first method, statistical machine translation, so character-level statistical machine translation. Which relies on the noisy channel principle, and it's a combination of 2 models. We have the translation model and the language model. The translation model is responsible for the adequacy of the translation. So it ensures that a sequence generated by the model is a good translation of a given source sequence. And the language model is the model that is responsible for the fluency of the output. So it ensures that a sequence generated by the model sounds natural in the target language. And in case of character-level statistical machine translation, we have, in the translation model, we have a phrase table, and the phrases in the phrase table are just sequences of characters instead of words. And in the language model, our anagrams will be sequences of characters instead of words. And now, as promised last year, we can now present our neural machine translation system, and for this I leave the floor to Tatyana.
You can hear me. Okay, great. Okay, thank you, Massimo. So I will introduce now the neural approach that we took for the normalization task. And the first thing which is important to realize is that the 2 components of the machine translation S&T system that Massimo has mentioned before, the translation model and the language model, they are still present in the NLT system, but they are fused together as a part of the neural architecture. And while in S&T we train these components separately. Now here we present the neural architecture that we used, and this is with which we have started with. And this is relatively standard encoder-decoder setting by now. So we use a bidirectional LSTM decoder here on the picture in order to encode the input sequence, and the LSTM decoder to produce the output. And here the decoder essentially acts as a language model over the characters on the target side of the corpus. And also standard, by now we use the soft attention mechanism, which allows the decoder to look at the parts of the input which are important for producing the output at each step. And on the right hand side we have the formulas for our approach, and we can go into math if anybody is interested during the discussion time. So now if you look at the output of the NLT system, then we can see that there is a room for improvement. And here we have an example for the input word itere. And during the decoding stage of the NLT system, the system produces the list of the normalization hypotheses which are ranked by the NLT system scores. And if you look at the top of the list for the input itere, then we can see that the NLT prediction itere, which has the highest score, is actually wrong. And the correct one, in this case, in diese, is in the list, but it's scored much lower. On the other hand, the word iterant, the wrong prediction, is something that we've never seen in the corpus, while we do observe the words in and dieser. So how can we give a signal to the system to use this frequency of the words that we do observe in the corpus? Well, we can combine the NLT scores over characters with the language model scores over words. And this is how we do it. We used an approach which we call synchronized decoding. And this is an approach that we've already used before successfully for a different but somewhat similar task of morphological segmentation. And so basically the algorithm allows you to combine several predictors which score on the different level, for example, characters versus words. And in our case, the algorithm modifies the decoding stage of the NLT system, which operates on the character side. And then the core of the approach is to guide the decoding so that it gives the signals to the NLT system where it should use the language model scores over words. And here we have an illustration for the algorithm, but unfortunately it's not enough time now to go through it. But if you are interested, then we can do it. I'm happy to do it during the discussion time. So now our experimental setup. Apart from the vanilla NLT and SNT systems, we've tried several approaches for training an additional language model. And we distinguish between two basic settings. The first one is what we call reuse. Basically refers to the setting where we reuse the training data that we have used for training NLT system. And as I showed before, the decoder of NLT system is already a language model over the characters over the target side. So we reuse the target side of the corpus in order to train a language model over words, so higher level units. The next setting, which we call add, is something more common, where you just add the additional data on the target side and train a language model over characters over this side and over this data and combine this with the system. And the last setting, what we call reuse plus add, refers to the setting where we combine those ideas together. So we reuse the target side data and train the language model over words, but we do this over the extended target side of the corpus. So we combine the original WhatsApp corpus target data with the SMS corpus target data. And the reuse settings are only applied to the NLT system because it gives us a flexibility to apply the synchronized decoding approach, while we don't have this flexibility in the SNT system. Now, regarding the corpus, we looked at the two versions of it. The original refers to the version that we got in the beginning, and here the emojis are replaced by the strings of characters, and the system has to learn how to copy those strings of characters. And In the modified version, we replaced those strings of characters back to the Unicode representation and treated them as an entry in the vocabulary. And we believe that this modified setting reflects better the situation where we have the scenario of normalizing a running text. So here are our results. What we can see here is, first of all, that both vanilla NLT and SNT system are stronger than our baseline. Then second, in the add setting, so adding the additional data helps both systems to improve further. Now, comparing the two systems, the NLT ensemble of 5 is already better than the best setting of the SNT. And now, regarding the NLT system, we see that both add and reuse setting help, but the best performance system is where we combine these two ideas together. And now, of course, one can try some combinatorial combinations of those settings, and we've tried some which made sense. However, they were still, the accuracy was still not that high as the one of the best system. And now I can give the word back to Massimo.
Thank you. We've done some error analysis, and we've singled out some examples in which the statistical system gives a wrong prediction and the neural system gives a correct prediction. So as you can see, the prediction of the neural system is the same as the reference, as the manual normalization. And we have three categories of possible causes of statistical machine translation errors. The first category is when the reference is very different from the source text, and so the statistical system has difficulty producing a correct output. The second category is foreign words. In this case, the statistical system forces normalization when it's actually not necessary, because the foreign word should be left as it is. And the third category is when one Swiss German word is normalized as two or more normalized forms. And we believe that in all these examples, the additional integrated word-level language models played a very important role in improving the translation of the neural systems. One interesting case, as you can see, we have highlighted it. The statistical system has learned a pattern, like the Swiss German IG becomes UNG in the normalization form, and it hypercorrects. It thinks it applies it all the time, even when it's not necessary. So, to conclude, we have shown that it is actually possible for neural networks to achieve state-of-the-art performance in text normalization, even when training data is of limited size. And we can achieve that by exploiting the flexibility of neural networks to be integrated, be expanded somehow with additional components. In our case, additional language models that operate at different organizational levels. So not only characters, but also words. And future work, some interesting things that might be worth trying in the future include the context for disambiguation. Because sometimes we have the same, one Swiss German word may have more than one normalization form. And if we use the context, it could help to resolve some cases of ambiguity. Learn the predictor weights as part of the neural model, because now what we're doing is just, we're doing optimization, basically, and we use the same weights for the whole corpus. And introduce copy mechanism for unseen characters. In some cases, the neural model makes errors when a character has not been seen during training. Like we've seen that with the emojis when they are not expressed as a description, but as a Unicode character, and they are unseen. The neural model makes a mistake because it doesn't copy them, which would be the best strategy in this case. Thank you for your attention, and if you have any questions,
Thank you for your presentation, and Questions? Start with Simon and then we can keep.
Small question. Limited size training corpus. Maybe I didn't catch it, but what was the size of your training corpus?
Oh, sorry. I go back to yeah. It was on. Sorry, you're right. It was on the table, but so we have basically for the WhatsApp corpus, which is the main corpus that we use, we have 54,000 alignment units. Whereby a unit is just, in most cases, a one-to-one alignment. So one word and the corresponding normalized form. And the SMS corpus is much bigger, but we use it only to train the additional language models, so only the target side.
That's a training side.
That's a whole data set. And then we split the 80% training, 10% development, and 10% test set. For both models, both for statistical and neural models. And we use the same split for all our experiments. So
Okay, let's move.
I have the same question.
Same question, but there are more specialists on processing Swiss German here, so please.
I guess that an important part of these ambiguities come from the fact that actually you treat many dialects.
yes.
And the knowledge that you probably can trust on is that if someone starts with Bernese, then he will finish it. So the whole SMS is in the same consistent dialect.
Yes.
So did you ever try to, because I mean, let's say you think that the L to U is only in Bern and not in others, so would you be able to use this?
Yes, right now.
Do you understand the question in the back?
Yeah, the question is if now we treat all the dialects together, and if we have the information of where the message comes from, and then we know that it belongs to a specific dialect, then we could use this information for better disambiguation. We're not doing that now. We're just consider all the dialects together. We've noticed that the systems, in most cases, are able to speak Bernese. This this pattern, U, L, is very common, and in many cases, especially the neural system, can identify it.
I mean, just the rules. I mean, the rules are consistent for a whole SMS message system. This is used.
Yes, that's a good point.
So basically cluster the rules for a particular dialect. There was a question there?
So the alignment units, did you do this manually that you normalize all the words, or where does this normalization come from?
It's been done manually. Yes. Yes.
But that was kind of before your particular project started, somebody had done this manually.
Yes.
Yes, exactly. So, yeah, we used.
Otherwise, there would probably still be others.
This WhatsApp corpus was created within the project WhatsApp Switzerland and was made available to us for this project.
Question?
Could you say a word on the generalization performance? Firstly, to unseen words in the same dialect that are already trained, or even to unseen dialects?
Yeah, we don't differentiate between dialects. So what we have noticed is that the performance compared to the baseline improves a lot on new words. As you can see, unique words, the baseline is 98%. It's a very strong baseline. So words that are always normalized the same way in the training set. And for ambiguous words, we have 81%, and new words 30%. That's the baseline. So what we hope that our models do is to improve this, because ambiguity is kind of inevitable.
It's the next step that we want to.
Yeah, there's some sort of ceiling that you can't go beyond that ceiling because of ambiguity. So we, all the improvement that we have was basically here, but we don't differentiate between dialects.
Maybe to add here is, if you split the words into seen words and unseen words, compared to the training data, then with the machine translation method, you improve for unseen words, because you learn this transformation, this local transformation, right? And then our additional method with the language model actually helps with unseen category, where on the target side, you have seen these words. So for example, 1 or 2 words on the target side, if you have seen them, then language model would help to filter out those. So that's like where those methods help. But regarding the ambiguous category, it's something that we want to tackle in the future.
Good. Thank you very much for your questions, and thanks for the speakers again for your presentation.